CLI and a cross-platform IDE for C and C++. Download now.
So this talk, we're going to explore the tools, libraries, and best practices that you should use to write idiomatic and modern CUDA C++ code. But first of all, what is CUDA C++? What are GPUs? And why would we want to use them? So show of hands, who here has written code that runs on a GPU? OK. Who here has used specifically CUDA? OK, cool. So what are GPUs? Modern CPUs and GPUs are both general-purpose processors that can run almost any kind of code. They differ in what types of workloads they are optimized for. So CPUs are optimized for latency. They have more powerful cores and threads, but less of them. They have less latency to access memory and more memory to access at the cost of much lower throughput. Now, GPUs are optimized for bandwidth and parallelism. They can run hundreds of thousands of threads. Their memory latency is higher, but the memory throughput is much greater. So how do we program a GPU in C++? Well, with CUDA C++ and NVIDIA's accelerated libraries. So what exactly is CUDA C++? Well, CUDA C++ is an extension of standard C++ for writing programs that simultaneously run on CPUs, which we call hosts, and GPUs, which we call devices. So in host code, you just write regular C++. You can use all of standard C++. And in device code, most but not all of standard C++ is supported today. For example, you can't throw exceptions yet. There are some restrictions about how host code and device code can interact. So for example, a variable on the stack in device code can't be accessed by host code. You don't have to write your CUDA C++ program from scratch. There is a diverse collection of CUDA accelerated libraries developed by wizards at NVIDIA that you can and should leverage. So these libraries have been carefully designed and tuned to provide speed-of-light performance. Before you write any CUDA C++ code, you should first check if there's a library that will work for your use case. And if there is, you should try it out and benchmark it. And if it delivers the performance that you need, then you should just use it. Don't reinvent the wheel. So now let's dive in with our first CUDA C++ program. So imagine we have a bunch of cups of hot water, or since we're in the UK, tea, at different temperatures that are recorded by a thermometer in each cup. And so we want to simulate how these cups will cool down. So we'll do this by applying Newton's law of cooling for a number of time steps. In standard C++, we would represent our cups with a stood vector of floats. And then next, we define our per cup cooling operator with a C++ lambda, which is just a way of defining a function object in C++. And then for each time step, we apply the operator to all of our cups using one of the standard C++ algorithms, stood transform. When we compile this standard C++ code, our compiler lowers each function and operation to the appropriate instruction set for the target processor. But when we're writing a CUDA C++ program, there are two different kinds of target processors, the host and the device, and each has its own different instruction set. So the CUDA C++ compiler in VCC will compile CUDA C++ code for different targets. But how does NVCC know what targets a particular function should be compiled for? Well, that's what execution space annotations are for. If you don't provide an execution space annotation, the function will only be compiled for host code, meaning the CPU. You can also explicitly request this with the host annotation. If a function only has the device annotation, then it will be compiled only for device code, meaning the GPU, and you won't be able to call it from host code. If a function has both the host and device annotation, then it can be used on both the CPU and the GPU. So now our operator can run on the GPU, but we still need to actually invoke it there. Execution of a CUDA program always begins on the host. Work must be explicitly launched on the device. The transitions between host and device are always explicit. you have to call a function that launches work on the GPU. CUDA C++ won't magically decide to run things on the GPU for you. Functions that are invoked in the device will stay on the device. You can't launch host functions from the device. So going back to our example, the work that we want to launch on the device is our std transform. We can launch this on the device using thrust transform. So it does the same thing as std transform, but in parallel and on the device. It takes one additional parameter, which is an execution policy, and that describes the user's requirement for how the algorithm can be parallelized. In this case, we're saying launch this algorithm in parallel on a CUDA device. Now, we also need to make sure that the data is accessible on the device, which we can do by switching from std vector to thrust universal vector. So thrust is a C++ parallel algorithm library. Its execution policy algorithms that we just saw were adopted by standard C++ in 2017. So those are the C++ standard parallel algorithms. So Thrust has implementations of those standard parallel algorithms for a bunch of different target platforms like CPUs and GPUs, and also a collection of extensions and additions to these standard algorithms. Thrust also has heterogeneous containers that behave like std vector, but store their contents in different kinds of memory that are accessible to different kinds of processors. So std vector's contents might only be accessible in host code, depending on the type of heterogeneous system that you're on. When you construct or assign to a std vector, that operation is done in serial, which can be quite slow if you're dealing with large amounts of data, as we often do when using GPUs. Now, Thrust universal vector's contents are always accessible in both host and device code. And operations on thrust vectors, like construction and assignment, are executed in parallel on the device. So Thrust also has a collection of iterators that can be used in conjunction with Thrust's algorithms to compose more complex computational patterns. If you're familiar with ranges, this is very similar. So standard C++ and Thrust algorithms typically iterate over sequences of objects. For example, the elements of a container. However, in numerical and scientific computing, we often want to iterate through indices, not objects, because we're doing something like a stencil. We can do this with Thrust counting iterators. So a counting iterator is constructed from an integer and represents the range of all integers from that integer onwards. So when dereferenced, it returns that integer. When incremented, it increments that integer. It's just like std views iota. By passing a counting iterator to a Thrust algorithm like for each n, we can iterate over indices instead of objects. Thrust also has a constant iterator, which will just repeat the given number forever. Now, iterators can help fuse together operations into beefier and more efficient work. So suppose that we want to transform some data with one function f, and then reduce it with a reduction op g. So there's two problems with this approach as shown here. By default, the Thrust algorithms are fork-join synchronous. So each invocation launches its work on the device and then blocks on the host until that work completes. So in our example, this leads to an unnecessary latency bubble, which can degrade performance. We're waiting on the host for the transform to finish before we can start on the reduce, before we can even launch the reduce, even though there's nothing that we need to do on the host with the result of the transformation. Additionally, we've had to allocate ON temporary storage for the transformation, which will waste precious device memory. GPUs don't have a ton of memory, and cause expensive and unnecessary loads and stores from device to global memory. So one way to address this problem is to fuse the operations together into a single parallel invocation, which can be done with a transform iterator. So a transform iterator takes some other underlying iterator and a function. And when you iterate a transform iterator, you get the result of applying the function to the values from the underlying iterator. So this is completely lazy. The function is only evaluated as needed when the elements of the returned iterator are accessed. So for example, here, f is not evaluated until the elements of temp are accessed in the reduction. Sometimes we need to combine together multiple inputs into a single iterator to pass to an algorithm. We can do this with the zip iterator, which takes any number of other iterators and produces tuples that are a combination of the values from the underlying iterators at the corresponding position. So for example, here we make a zip iterator from x and y. And when you dereference this iterator the first time, you'll get a 2-element tuple, x0 and y0. And if we increment it and dereference it again, then we'll get x1 and y1. You can also use zip iterators to invoke algorithms on overlapping windows or stencils of elements. For example, here, we're constructing a zip iterator to the adjacent pairs of elements of x, and then applying the function f to each pair with for each n. So f will be invoked with x of 0 and x of 1, and then it will be invoked with x of 1 and x of 2, etc., until the end of the iterator. So if you're familiar with std views adjacent, this is very similar. Or std views pairwise, I think is the exact equivalent called. So let's look at another example that combines all of this together. So suppose that we have two vectors of the same length, a and b, and we want to calculate the maximum difference between corresponding elements of each vector. So we can do this by first calculating the difference between each two elements, and then doing a max reduction of those differences. So we start off with our two universal vectors, a and b. And then we calculate the difference between each two elements of a and b, storing it in a temporary vector that we've allocated. Finally, we do a reduction of the differences with maximum as the reduction operator. We can improve this by replacing that transform with a zip iterator and a transform iterator. So the zip iterator produces 2-element tuples of each corresponding element of a and b. And then the transform iterator takes that zip iterator and applies a lambda function to it that unpacks the tuple and computes the difference between those two values. Now, this pattern of transforming and then reducing is quite common and it's very powerful. So Thrust has a single algorithm called transform reduce that does the fusion with the transform iterator for you. It's equivalent to the code on the slide before, and actually that's how it's implemented internally in Thrust. So this is known as map reduce in some domains. Now we've used two new facilities in this example, CUDA std tuple instead of std tuple, and CUDA maximum, which is a function object, instead of std max, which is a function, and thus would be a function pointer if we're passing it into an algorithm. So these are facilities from Libcu++, which is CUDA C++'s foundational library and NVIDIA's C++ standard library. So CUDA C++ uses your host platform's C++ compiler and C++ standard library for host code. So GCC, Clang, MSVC, etc. is what's going to be used to compile your host code within BCC. The facilities in the std namespace, therefore, come from the host C++ standard library, and they're not designed to be run on GPUs. They're all host only, and we can't go and modify or mess around with them. And so Libcu++ provides a subset of the C++ standard library in the CUDA std namespace. And these facilities can be used in and across host and device code. Libcu++ also has many extensions to the C++ standard library, as well as modern C++ APIs for the CUDA runtime and device-side facilities. And you can find these in the CUDA : namespace. And beta features that are not yet stable are in the CUDA experimental or CUDA X namespace, and we'll see a couple of those a little bit later in the talk. So now let's take a look at one of the most popular kinds of extended algorithms in Thrust, which are by-key algorithms. So by-key algorithms will divide the input up into contiguous groups and invoke an underlying algorithm on each group. So they're also known as batched or segmented algorithms. For example, suppose that we have a matrix and we want to sum each row of that matrix. To use a by-key algorithm to solve this problem, we must first create a range of keys that define the groups. So each set of consecutive keys that can pair equal defines a group. In our example, all elements in the same row should have the same key, and the value of that key can just be its row index. We don't have to materialize these keys in memory. We can generate them on the fly with thrust lazy iterators. So we use a counting iterator to generate the linearized location of each element, and then we determine its row by dividing by the number of columns using a transform iterator. Next, we'll need some storage for the sums for each row. And then we'll invoke our by-key algorithm. In this case, we're going to use reduce by key. The first parameter that it takes is the input for the keys, which will be those thrust lazy iterators that we just generated. Then we'll have our values input, which is our matrix M. So the underlying algorithm, reduce in this case, will be applied to the values within each group. So next we have our keys output. By-key algorithms will copy one key for each group since they all compare equal, and it's just going to be the first one in the consecutive sequence, and it'll be copied to the key output range. But in our case, we don't actually need the output keys because they'll just be the same as the index of each sum in the sums vector, and writing them unnecessarily will waste precious device bandwidth and memory. So we can use thrust discard iterator to ignore the output. So thrust discard iterator is a thing where when you dereference it, it returns this special object that just does nothing when you assign to it. So it will just ignore whatever you try to output to it. So then finally, we have our values output, which will just be our sums vector. And then that's it. We're done. We've got a row sum. There are a bunch of different by-key algorithms in Thrust, including reductions, scans, sorts, unique, merge, and set operations. And these are particularly useful for batching up operations that you need to perform on different groups of data, which will enable more efficient parallel processing. Instead of launching, in pieces of work in the GPU, you can launch one big, beefier piece of work, which is going to be more efficient. So now let's move on to another example working with multidimensional data. So let's simulate my oven, which has a heating element on the top and on the bottom. So that's a picture of me during the pandemic with an apron that one of my interns got me that says, I usually cook C++ to standard, but today I'm doing cakes and a bunch of stuff I cooked during the pandemic. So we're going to simulate my oven on a 2D grid by solving the heat equation numerically with a 5-point stencil. So our solver function will take a thrust execution policy, the dimensions of the grid, and two universal vectors, u, which represents the current state, and v, where the next state will be written. We'll use a thrust for each n over a counting iterator to implement our stencil. The for each n lambda will need to capture the grid. However, we can't just capture those universal vectors. If we captured them by value, we'd make a copy, which is not what we'd want. And we can't capture them by reference because while the contents of the vectors can be accessed from the device, the vector object itself may not be in memory that the device can access. So we can't take a reference or a pointer to it. So instead, we obtain pointers to the vectors and capture those. It's a little unpleasant. The first thing we do in the body of the lambda is reconstruct the multidimensional indices from the linear index. Next, we need to check if we're in the interior of the grid, in which case we need to apply the stencil. And then here's the stencil computation itself, which is a little bit scary and has a lot of indexing math. But that's what numerics is. And then if we're on the boundary, we don't change anything. Now, there's a few different unfortunate things about this code, such as the repetitive and error-prone multidimensional indexing. And what we really want here is a proper extraction for multidimensional data. And I'm glad to tell you that it only took me 10 years, but we got one into standard C++, which is MDspan. So MDspan is a non-owning handle to multidimensional data. It's basically a pointer plus metadata. The layout of an MDspan is configurable, and the dimensions can be specified either at runtime or at compile time, and they're expressed through something called a extents object, which we'll see a little bit later. Now, copying MDspans is cheap and trivial because you just copy the pointer, not the contents. MDspan has a powerful slicing facility that's called sub-MDspan that will produce new MDspans that view a subset of the same underlying data. If you're familiar with stood span or stood string view, this is very similar, just for multidimensional data. So let's rewrite our heat equation solver to use MDspans. So instead of taking universal vectors and obtaining pointers to them that we can capture, we just take MDspans, which can be captured by value and copied to the device. So we replace the manual indexing with calls to MDspan's index operator with the multidimensional coordinates. So now let's write a function to set up the initial state. It will take a policy and an MDspan to initialize. We can break the grid down into 3 different regions that we need to initialize, that we need to set. So we'll use sub-MDspan, that MDspan slicing operation, to obtain MDspans to these 3 regions. So sub-MDspan takes an MDspan and 1 slice specifier for each dimension, which indicates which indices from that dimension should be selected. So a slice specifier could be a single index, a range of indices, optionally with a stride, or the entire dimension, which is indicated by full extent. So the first 2 regions that we need are the row at the top of the grid and the row at the bottom of the grid. And then the last region is the interior point, which is just everything except for that first and last row. And then we want to set the top and bottom row to a high temperature, and we want to set the interior region to a lower temperature, which we do here with thrust fill in. So now we'll write the time stepping loop that repeatedly calls the solver. So we'll output the state of the system periodically during the loop. So after every compute steps evaluations, we'll do 1 output. And in total, we'll do write steps times compute steps iterations. So we'll start by setting up our 2 universal vectors and constructing MDspans to them. And then we'll initialize u with the function that we just wrote. And next, for every write step, we'll save the current state by calling some save to file function on u. And then for every compute step, we'll call our solver function with u as the input and v as the output. And then we'll set the new state from the solve as the input for the next solve by swapping u and v. So as we discussed earlier, thrust algorithms are all fork join synchronous by default. So they launch the device work, and then they wait until that work has completed before they return to the caller. And this introduces unnecessary waiting on the host and underutilization of the device, because we can't launch the next piece of work until the first one finishes. We want to be able to overlap the latency of launching device work, which is fairly high, so that our GPU will always have work in its queue and reach maximum utilization. So that means we need asynchrony, and for that, we'll have to change the execution policy that we're using to thrust. So the thrust CUDA par no sync policy will cause algorithms to not wait for the device work that it launches. So the algorithm invocations will return immediately, and the caller will be responsible for synchronizing later. So in our case, we'll need to wait on all device work every write step before we call save to file to ensure that the last compute step has completed before we begin writing. So this is a good start, and then the next step is going to be to use CUDA streams. So a stream is a chain of device work that is executed in order. You can think of it like a queue. You can have thrust launch work on a specific stream by passing the stream to the on method of the execution policy. So here we asynchronously launch a for each applying F and a for each applying G on the device. The F for each will complete execution before the G for each starts. So a stream can record an event that host code can synchronize with, waiting for all work up until that event to complete. So you can do this in code by simply calling wait on the stream object. In this case, it'll wait for both for eaches to complete. If we instead wait before the call to the G for each, then we'll only wait for that F for each. You can create multiple streams that run concurrently on a single device, just as you can run multiple threads concurrently on a single host. So streams can wait upon other streams through events. You can explicitly record an event on one stream with the record event method, and then you can have another stream wait for that event by calling the overload of wait on a stream that takes an event. So note that the host will not block on the event when you call this particular overload of wait. It will just tell the stream to block on the event and return immediately. So you can use streams to control what specific device your code runs on. By default, they're constructed on the first GPU in your system, but you can explicitly construct them on any device on whatever system you're on. Dependencies can be established between streams that are running on different devices. So let's revisit our heat equation example and add streams. So we'll create a stream, define an asynchronous policy that will run on that stream, and then we'll use that policy in all of our calls to thrust. So now instead of waiting with all work on the device at the start of each write step, we only have to wait for the work that's on our particular stream. Now, there are, unfortunately, today some limits to thrust's support for asynchrony, but these are going to hopefully be resolved in the near future. I've got pending PRs for most of these. So it works great for algorithms like for each and transform. But some thrust algorithms either return a result that depends on the computation, or they allocate temporary storage for the computation. So today, these interfaces will always block even with the par no sync policy because they have to. So for example, inclusive scan, it returns an iterator to the end of the output. Now, this doesn't depend on the computation because we can just compute it beforehand by incrementing the output iterator by the size of the input. Thrust only takes random access iterators, so this is perfectly fine. However, unlike for each and transform, scan algorithms require temporary storage. And thrust has to allocate and deallocate this storage before the algorithm returns, which will block today even with the par no sync policy. However, CUDA does have an async allocation API that was added a couple of years ago, and we're working on changing thrust to use that so that this will, in the near future, be asynchronous as well when you use the par no sync policy. Now, algorithms like copyif return an iterator to the end of the output, but that will depend on how many elements pass the predicate, which we won't know until the computation is complete. So these kinds of algorithms are implemented in terms of a scan, which means that they also need temporary storage. So thrust has to block before returning from these algorithms, even with the par no sync policy. Reduction-based algorithms like reduce, countif, findif, and max element return the result of the reduction, which means that they have to block. They also need to allocate temporary storage. So we're planning on adding additional versions of these algorithms, like a reduce into that returns void, but takes an output iterator and will write the reduction result to that output iterator. And that's how we'd solve this problem. But if we need asynchronous versions of these algorithms today, there's another somewhat lower level CUDA C++ algorithms library that we can use that is asynchronous from the ground up. And that is Cub, which is the CUDA C++ algorithm authoring toolkit. So Cub provides the cooperative building blocks for writing your own device-side kernels, or your parallel algorithms. But that's not really the focus of our talk today. But if you're interested in that, there's a great talk at NVIDIA's GTC conference. There's a link there that dives into more of the details for how you can write your own CUDA C++ kernels. I'll also link some learning material at the end. But today, we're going to focus on CUB's device-wide algorithms, which you launch from the host just like Thrust. So as I said, CUB is a little bit lower level than Thrust. We just discussed how some Thrust algorithms need to allocate temporary storage, for example, reductions. So we implement GPU reductions today with two passes. The first pass divides the input up into chunks, each of which is handled by a block of threads, which will collectively reduce the entire chunk to a single value that is stored in a temporary array. A second pass will then use a single block of threads to reduce the aggregates in the temporary array to a single result. And so this avoids any need for any sort of global synchronization or atomics. So with Thrust, the temporary array allocation and deallocation is done implicitly within the algorithm. Now, CUB is asynchronous by design, so it doesn't return the reduction result by value from its reduce algorithm. Instead, it takes an iterator and assigns the reduction result to that iterator. So when we call a CUB reduction, we need some device-accessible storage for the result, which we create here with a universal vector. With CUB today, we must allocate the temporary storage explicitly. But first, we have to determine how much temporary storage we'll need. And this is not trivial to figure out because it will depend on the algorithm, the data types, the operators, the device architecture, etc. Since you need the same information that you'd invoke the algorithm with to compute the temporary storage size, we use the same interface to do both. So the first two parameters to a CUB algorithm are a pointer to temporary storage and a reference to the temporary storage size. And if the pointer to temporary storage is null, then the algorithm will not be invoked, but instead the temporary storage size will be computed and assigned to that reference that you passed in for the temporary storage size. And so then after that first call, we can need to allocate the temporary storage size, which we can do because we've now figured out how much we need. And we do this with a vector of CUDA stood bytes. And then finally, we call the algorithm again, passing in a pointer to the temporary storage this time. And the work will be asynchronously launched on the device. So let's rewrite our heat equation solver from before to use CUB. So CUB has a for each algorithm just like Thrust. Since this never needs temporary storage, you don't need to pass a temporary storage pointer or size in. CUB algorithms don't take execution policies, so we don't need to pass in an execution policy anymore, but we can specify what stream to run on. And it's always the last argument to a CUB algorithm. So we'll just pass that in instead as a stream ref, which is a non-owning handle to a stream. We're still using a counting iterator here. Thrust iterators work great with CUB, and it's common for people to use them together. Likewise for Thrust vectors. But CUB has a better algorithm for this particular use case of iterating an MDspan, for each and extents, which takes an MDspan extents object instead of an iterator and calls the operator with the multidimensional indices. And so you don't have to reconstruct the multidimensional indexing yourself, which reduces complexity and increases performance. CUB will do that reconstruction for you if it's needed, or it could launch the work on a multidimensional grid of threads and sort of like a nested for loop and avoid the need for any reconstruction whatsoever. So throughout this talk, we've been using Thrust universal vectors for device-accessible storage. Now, universal vectors are implemented with CUDA unified memory. So let's go under the hood and see how it works. A universal vector is accessible from both host and device code. But host and device have, in some cases, different physical memory. So where do the contents actually reside? Thrust's universal vector's contents will start on the device because that's where they are initialized. And if we then access an element of the vector from the host, the CUDA platform may have to migrate the data from the device to the host. And the mechanisms for this transfer will vary between platforms. In some case, it will go through software. In some case, it will go through an operating system. In some cases, it'll go through operating system through the page tables. In other cases, it's completely handled by special hardware. On a system with an NVIDIA CPU and GPU, like an embedded platform, there may not need to be a migration at all because the CPU and GPU may share the same memory. Migrations won't move the entire vector, just a part of it. And it won't be at the granularity of a single element. Chunks will be migrated at a time. Some amount of pages of stuff will be migrated. So if there is a migration, then we end up with 2 copies of that element and any other elements that were speculatively migrated. There's a copy in host memory that's good, and then there's some stale copy in device memory that might get paged out at some point. And if we access a different part of the vector later, then it will trigger another migration. And if we later access that first element from device code, then we'll have to migrate the element back. With CUDA unified memory, transfers are implicit and piecemeal. This has advantages. It's simpler to program, and it allows you to oversubscribe GPU memory. You can create a universal vector that is the size of your host memory, not limited by the size of your device memory. If we're not accessing the entire contents, if we're doing some sort of sparse access like to a database, then this may be more efficient. However, if we're iterating through the entire vector, it will be less performant to migrate the vector piece by piece instead of doing it all at once. So unified memory is just one of the options available to us. It's the most user-friendly, which is why we start with it. But we can also allocate memory that is tied to a particular target. So host vector will allocate memory that can only be accessed in host code. And device vector will allocate memory that can only be accessed in device code. To transfer data between memory spaces, we can use thrust copy, which works just like std copy. But unlike std copy, thrust copy understands different memory spaces and the various ways of moving data between them, and it will dispatch to the correct and most optimal mechanism possible. So if we take a look again at our heat equation code, our save to file function will access the entire U vector on the host, and it will cause an implicit piecemeal device to host transfer. Instead, we can create a staging buffer in host-only memory and explicitly copy from our problem state in device memory to the host memory staging buffer with thrust copy. Now, not only is our memory transfer more efficient, but we are also overlapping the compute with the I/O. So our code will first initialize the problem state asynchronously on the device, and next we'll enter the outer right loop on the host. Next, every write step, we start by copying U to buff. And then we immediately wait on the stream, ensuring that any previous compute and the copy have completed before we continue. Next, we asynchronously launch our heat equation solver compute step times on our stream. And then on the host, we start outputting the staging buffer at the same time as the heat equation solves are happening on the GPU. And then we repeat this for every iteration of the outer right loop. And if you want to learn a little bit more about how to overlap compute and I/O, there's a few more steps to optimizing this, including another staging buffer. And that is covered in a tutorial on our Accelerated Computing Hub. So we've only talked about a few of the many CUDA accelerated libraries today, but there's many more to explore, including math, machine learning, data science, simulation, physics, I/O, networking, and device-side programming. And I showed you some version of this slide before. We've launched a whole new curriculum of CUDA C++ content this year, including a lot of learning materials, tutorials, and notebooks.